So today we are going to discuss more on synchronization issues with the operating system, how we are going to handle. So what is critical section problem? Let us suppose I talk about the source code is incrementing some variable X, which is basically shared or incremented by more than one processes. So this is a source code, and this source code would actually be converted into assembly language or your machine code as load R, add R, and store R. So there are three basically instructions that would be executed when this X is equal to X plus C would happen. Now let us suppose there are two processes which are going to add in or update the location of the variable X. So here is process P, which is basically adding X is equal to X plus 1. So this is one instruction in process P. Then we have another instruction in process Q, which is X is equal to X plus 2. When we are adding and augmenting updating the shared location, so variable X is used by two processes. So then such problem is called critical section problem, because this is not going to be a single processor system. It may be multi-core system. There are concepts of concurrency, and also there are processes which run on parallel, because we talk about multi-core environment and hardware also. It may be possible at same time two processes are running. Now, the synchronization problem is that if we have shared space or shared update to one variable, then those processes should not actually run, concurrently or parallelly, but they should follow some sequential order. So synchronization problem is to solve how to solve and make the processes to run in sequential order. That is the whole objective of this chapter. How to enforce multiple processes which are running or updating one particular value on a variable, how to run them in a sequential order. So let us suppose we talk about these two processes, P and Q. Then we have, if the sequential process goes like, what would happen? First P, let us suppose P starts executing. So it will actually load the X value into the register 0, then add it with 1, and then store it back to the basically the register value into the variable X. So this is one process which executed. Now if it is sequential, like one happens and other happens after it, then Q would actually fetch the value which is currently 1, then add 2 to it, and then store back the result 3 back to X variable. Now this is happening sequentially. This is what is an expected behavior. When two processes are executing the same, updating the same variable, they should be, the effect should be atomic or consistent. But in case of interleaved execution, when we have the processes running concurrently, we don't know which process would go into waiting state, which process would have highest priority. We don't know about that. So basically it is running conditions. It may be possible that they are running in sequential, but it may be possible they are basically running and executing as interleaved. Now what is interleaved execution? RP means register for process P, and RQ means registers for process Q. Now P started running, so P loaded 0 value and load RP with X. So X was 0 initially, and then it will load RP with X. After this instruction, the process Q also started loading its register. It load RQ with X. So now it is basically 0 again. So both are now having 0, 0 into their registers. Then because the instructions are interleaved, and it may be reordered also, that we are going to discuss next. Add RP is equals to 1. So this would actually add 1 to that particular register, and simultaneously another process would be adding into RQ. They are not doing it to QX, but to RQ they add, and then process P is actually writing RP into X variable back. So here are three processes: load R, load X into R, add R with C and store R into X back. So this is the last step. Now when the process P stores RP into X, it will be 1. And when process Q would be writing and storing back RQ into X, it will be 2. Now this is not expected answer. So this becomes a critical section problem. When we are not sure about what would be the consistent output of the two processes which are executing or updating the same variable. We don't know about that. That becomes a critical section problem. In that case, what we try is we should be having some mechanism by which we can actually control this and avoid this situation. And that's why we discussed about Peterson solution, which works on two processes if they are sharing the same space. Now here we start a discussion about that. It basically works with the two variables, flag J and turn. So these two variables are used to basically enable the synchronization between two processes. So we discussed about various use cases and see that what would be the consistent state. It means that this Peterson solution allows only one process to enter into the critical section whenever like both try to enter and acquire the same variable. So that's one thing. Now we are moving toward what other solutions are, but there are certain problems with Peterson solution for modern computing paradigms or architecture. Why? Because in modern computing architectures, it is also allowed to reorder the basically the instructions. It may be possible that instructions may be reordered, and that's why Peterson solution is not guaranteed to work on modern architecture. So let us suppose we have two things, Boolean flag and then int x is equal to variable. So these are shared variable between two threads. Now when thread 1 performs the statement, what it is doing, it is waiting while flag is not true. It is basically waiting here. Otherwise, if flag become true, it will come out of the loop and print x. So thread 1 prints value of x, whereas thread 2 loads the value of x. Now the expected behavior is that thread outputs the value 100 for the variable x. So if thread 1 started processing early, it will wait till the flag is not true, and once flag become true, so it is basically printing x. Now if T1 starts early, it will keep on looping and waiting. So it will be waiting. Once T2 start execution and make flag is equals to true, then our T2 would start execution. So this is how the process dependency is maintained basically. Now if we reorder these instructions, then what would be the situation? Like there are no data dependency between the variable flag and x. So in that case, it may be possible that processor may reorder the instructions. Let us suppose the thread 2 that the flag is assigned true before the assignment of x is equal to 100. And what would happen? Like I go back now here. Let us suppose in this situation, flag become true early and x is the second statement now. In that case, what would happen? If flags become true, this process, this thread which is waiting, the T1 would start execution, and this will start executing and it will print either 0 value or the garbage value, because here, we have initialized here, so it will be x is equal to 0 value would be printed by x because flag is already true without updating the new value. It may be possible that these two statements may also be reordered. So in that case, we would be having print x and while flag. So in that case, what would happen if this is going as is and there is no reordering? Then it will print x is equals to 100 without waiting for flag to set true. So that is one situation. If this is also reordered, then it will again print x is equals to 0. So I mean to say that the modern processor can reorder the instructions, and those can lead to the failure of Patterson solution. How that we are going to discuss now. So how does this affect the Patterson solution? Let's see. Go back to this. Okay, now this is the situation. Now if in case these two instructions are executed first, like they are reordered, so turn is equal to J and flag I is equals to true. So this is how the instructions are reordered. In that case, what would happen? In that case, what would happen is, let us suppose process P0, process PI started executing and it made turn is equals to 1. Turn is equals to 1 now, and then the process P1 also started executing and it made turn is equals to 0 and flag is equals to, let me draw this again, that would be I think better. Let us suppose this is process PI and this is process PJ. While true, what would happen? I have swapped the instructions. Here it is I, and then while flag J is and turn is equals to, so this is while loop, and then we have critical section. For PJ, while true, turn is equals to I and flag J is equals to true, while flag I and turn is equals to I, it keep on waiting. So this is the thing now. Now if this is the case, what would happen? Let us suppose this would make the process P0 would make turn is equal to J. Now here is a thing. Turn is equal to J. Now, okay. And then process P1 made turn is equals to 0 and flag is equal to true. Here is the interleaving basically. Here is interleaving. In that case, let us suppose this is true first, this is done afterward, and if the turn is equals to this particular value J, and this would actually fail and our process PJ would start into critical section. Okay, I'm just discussing on let us suppose process P0 made turn is equals to 1 and then this is turn 0. So there is basically the value change is there. So what would happen here is the process this would actually enter into the critical section. How? Flag I is not true. Basically flag I is not true. Yeah. So what would happen? The flag I is not true. Turn is equal to I. This is true, but this is not true. So in this case, process PJ would start into the critical section, because what would happen? Flag I. Here flag I is not true. So in that case, basically the flag would actually enter into the critical section. So what would happen is, now in this case, this is not true. So that's why it enters into the critical section. Okay. Now, meanwhile, what would happen? Flag 0 is also made true. Flag 0 is also made true. In that case, this is true and this is also executed on the process P0. So these two situations, because this has become 1, this has become turn has become 0, and then in that case this would also start executing, because what would happen is turn has been made 1 for this, and this would actually also start entering into the process. So what would happen? I mean to say, because of the reordering, the two processes would start execution into the critical section at same time, and this reordering creates a problem for the processes to be executed. So this situation would be handled by another process, or the next what we are going to discuss based on the hardware support for synchronization. So now there are basically the Patterson solution is software solution. So what is required, that there should be some support from the hardware. And in case of the hardware, we have 2-3 methods that we are going to discuss. And in many system provided hardware support for implementing the critical section code. The solutions are based on the locking mechanism, so protecting critical sections by lock. So there is a lock provided for critical section. So whenever some process wants to enter into that particular section, it should be basically acquired first, and then one can enter into that particular section. So if one process has acquired, all other processes which are waiting for some to enter, they should wait till the time the process one is not completed or out of that critical section. So it is basically acquiring the lock and then releasing the lock. So when some process wants to enter into the critical section, now you know what is critical section. It's basically the shared variable update. So when somebody and some process wants to enter, it should be acquired by a lock. So this is the process. Now in uniprocessor, we could disable interrupts. So one method is that we can easily like the process, if it is uniprocessor, the interrupts could be blocked, because interrupts are basically creating preemption. So whenever a process has to take the lead or higher priority process come, it basically preempt. And how it preempts? It's basically send the interrupt. So in that interrupt, your process would be put into the low priority, would be put into waiting, and then or back to the ready queue, and then the higher priority would start running. So if we have only one process running without interruption, then there would be no problem of this inconsistent data, because every process which started would complete without any other process which is running. For uniprocessor system or single processor system, this system could work very well. Like we can stop or disable the interrupts whenever some process enters into the critical section. But when there are multiprocessor system, this mechanism of disabling interrupts would not be a good, because we have to disable interrupts for all the processors, and which would make the system very inefficient. So rather than this, there is a concept of special atomic hardware instructions are designed. Now those atomic hardware instruction means that once they start running, they run to complete. So those are hardware instructions. They are non-interruptible. They are basically hardware instructions, not the software instruction. So the software solution or developers, they use these hardware instructions to enter into the critical section, because they are themselves non-interruptible. There are three methods. First is memory barriers. So the memory barriers is if a system may reorder instruction, the policy can lead to unreliable data states. And if we have chosen not to disable the interrupts, then it is possible that the reordering of instruction can lead to undesirable results, even if the impact what we have seen is only for one difference, like there is only one update missing. But that could lead to be a very problematic situation if the same thing is happening for your banking solution. So whenever you withdraw something, you add in something, and there is an inconsistent state of your balance, that would be very, very dangerous situation. For such, there are some mechanisms which are used. One is the memory barrier. So in the memory barrier, we used memory model. So memory model says whenever a process basically whenever a modification is done to a memory location, one process immediately visible to the other processes. A weakly ordered is whenever there is a modification to the memory on one process, or may not be immediately visible to another process. So this memory model is used for handling the reordering of instructions by using memory barriers. So what are memory barriers? Those are basically used, like this is the hardware instruction. So in this would actually place a memory barrier between the instruction which you think could be a problem, which could create a problem for basically the reordering of the state. Now, what would happen if we add a memory barrier operation to thread 1 while flag is not, then memory barrier, then print? We guarantee that the value of flag is loaded before the value of X. So what memory barrier does, it basically makes sure that the instructions, if they are reordered even, the memory barrier ensures that the store process is completed in the memory and visible to other processes before the future load and store operations are performed. So this is the situation, like what would happen if, even if there is a reordering happen, this memory barrier would actually make sure that the flag, the correct value of the flag, is already loaded into it, so that at least we are into the consistent condition. So similarly, we can put the memory barrier here, which would ensure that this value X must always be loaded before this flag goes true. So this is one concept of basically handling the reordering of the statement. If we ensure that the assignment of X occurs before the assignment to the flag, the memory barriers are considered good, and they are also very low level operations which are typically only used by kernel developers when writing their specialized code to ensure mutual exclusion. So this would actually enable us the mutual exclusion of using the data set or shared space. Now moving forward, we have another instruction which is called test and set instruction. This test and set instruction is atomic, means it is an uninterruptible unit. It run whenever it executes to the full, and this basically the test and set instruction is basically having this code. So what it does is it takes the target value into a temporary variable, then update the target value to true, and then return the previous value of the target. So let us suppose your previous value of target was false, then it will make RV equal to false and then update the target value to and return RV. So false would be returned here. What it does is it test, set, and return the previous value of the target variable. This could actually be used for locking mechanism as compared to what we did for the Patterson solution. If you understood that clearly, it is very easy for you to understand it here. So let us suppose if two test and set conditions instructions are executed simultaneously, each on different core, this mechanism would make them to be executed sequentially in some arbitrary order. So we don't know the order which would execute first, but this is for sure that they will be happening sequentially. And if the machine supports this instruction, then we can implement mutual exclusion by declaring a Boolean variable lock, which is initialized to false. Now let us suppose your lock initially is false. When it is initially false, so while test and underscore set, it is passing as lock is equals to false. Now this would be passed and this particular function would be executed, which is a atomic function. So what would happen? This test and set would return false and set the lock to 1. What would happen is, now this is a function which is, you can say, hardware instruction. This is hardware instruction. Now this is atomic. So atomic means it will run to its uninterruptible unit of code. Okay, now one thing is clear. Now the function test and set is doing that it takes the target, any variable, then creates a Boolean temporary variable RV, takes the value of target to RV, and then update the value of target to true and return the previous value which is saved in the RV back to the function. Now let us suppose we are having lock is equals to false. There are processes. So initially there are two processes which want to acquire the lock. Okay, so the lock is 0, false first. Whenever this function is called, this lock is false, the target, the initial value is false, it will make RV is equals to false, and the new value of the lock is true, and return what? When this return false, this infinite loop would actually terminate, and then this process P0 would enter into the critical section. Let us suppose there is another process P1 which wants to enter into the critical section. Now what it will do, it will run the same code. while test and set and lock. Now new value of lock is already made true here. Now when it will call this function, what would happen? This will call this function again. I'm talking about P1 now, P1 process. This has same instructions here. Now Boolean target value is true, Boolean RV value is true, and target value is true. Now that's the same target is true, and return value is true. So when this is true, the while loop here will keep on executing. So what would happen? It keeps on executing and wait till the time lock goes, false. So coming back to process P1, which has got this lock, which has passed this while condition using this locking mechanism, and in that case, the locks, once it completed with critical section, it made lock false. And once this lock is false, this particular while loop, the process P1, for that now lock's new value is false. So when it comes back here, which is checking for this particular condition, now false, new value become true and returns false. So when this returns false, so whatever condition inside is false, this is the only this is only the logic, like why we want to synchronize. There are multiple processes which want to acquire the to go into the critical section. Now you know what is critical section. We have to stop multiple processes to enter into the critical section. For that, in Patterson we used this while loop, and in that we used two variables, flag and turn. But for modern processes, it may be possible that flag and turn could be reordered. If flag and turn reordered, it may be possible that two processes enter into the critical section at same time. Now, if they enter into the critical section at same time, then the problem remains the same. Although it may be rare, but the problem remains same. The data would be inconsistent. So in that case, there are hardware instructions. Those can be used to stop those basically, things. So what has been implemented? There is a test and set hardware instruction or a function which is atomic. So when it start running, executing, it is uninterruptible. Because it's hardware, so hardware knows how to implement that. We start with single variable now, which is lock. Now lock initially is set to false. Like there are two processes, P0 and P1, P0 and P1. P0 wants to enter into the critical section. P1 is doing something else. It is not going to enter into the critical section. Now what would happen? This will run this particular condition, this condition, while test set lock. Now lock is false. So it will get past this while loop and then goes into the critical section. Once it completes the critical section, lock got back to the false. Then there is P1. P1 is not contending for the lock, so there is no contention. If they both try to acquire the lock at same time, one would be able to do it, and ultimately they would run sequentially. So either P0, then P2, P1, or P1 first, then P0. So there is an sequential ordering we enforced using a lock mechanism. Now the second instruction we have is compare and swap. This instruction is also just like test and set instruction, but it has two words, operates on two words atomically, and it used to swap those words basically. So rather than working on a single variable lock, now it is working on two words. Let us see what those two words are. The function here is, this is a hardware function, run uninterruptible. Compare and swap, it takes int value, it takes expected value, and then also the new value. What would be this value would be? So the int temp would take the current value. If the current value is equals to the expected value, then the new value would be updated. If this value is not equal to expected value, then new value would not be, this would not be implemented by this. So this is basically a swap operation. Okay. If this value is equal to this, then swapping is performed. If this value is not equal to this, then swapping is not performed. So that's a simplistic thing. And returns what? The previous value of this variable value. Now I repeat again. Try to like what I'm saying is this is int value. We capture that into temporary. Then we update the value of this variable based to the new value with this one, and return the previous value of temp what we did in test and set also. Okay, now how that would be used for critical section. Now this would be used for mutual exclusion. Mutual exclusion is what? Only one process can enter into the critical section at one time. So that is mutual exclusion. Okay, which is mutex. So the global variable lock is declared. Now what they are going to use? A lock variable, declare and initialize to 0. So before two processes are sharing the space, we declare lock is equal to 0, and then compare and swap is set. The first process that invokes compare and swap set lock to 1. How that would happen? So this is a while condition. So while compare and swap and lock, we pass in the value of lock, which is initially to 0. If this value is equal to this, the value of lock would be set to 1. Now, if this value is 0, this will be set, this value is equal to this will be set to 1. Okay. So if int now here, int value is equal to expected value, it means we are updating the value of lock. So lock would be 1 here. Okay. And return what? Temp previous value. So what was the previous value? Return 0. So this will handle 0. So while compare and swap, lock's initial value is 0. We have compared this with the expected value and then give the new value. If this is not equal to 0, if this is not equal to 0, then it will keep on running. While compare and swap for the first process, because lock was 0, so it would return 0. So 0 is not equal to 0. The condition becomes false. So now it will enter into the critical section. So now let us suppose second process wants to acquire, which is already, for that the lock is 1. So let us suppose another process P1 tries to run the same code. Now for that the lock, because P0 is already into critical section. So P1, now for P1 the lock value is 1. It will do this. Now lock value is 1, 0, 1. So what would happen? Now here, this is 1, this is 0, and this is 1. So as we know, as we took now, temp is equal to value. So value is 1. If value is equal to expected, this is not equal to, so this would not be executed and temp would be returned. What would be returned? 1. So in case when this is returning 1, this whole piece is returning 1, which is not equal to 0, condition will become true, and the process P1 keeps looping. Once the process 0 is out of this condition, it will make lock 0, and then your P1 can enter into the critical section. I hope this is clear also. Okay, now another situation is that we have to take care about the bounding waiting. There are 3 things that these synchronization things should allow. One, that mutual exclusion should be happening. Other is the progress should be there. So each process should be allocated to the critical section. And then the third is bounding time. So there should be some given time by which your processes should be given, should be allowed to enter into the critical section. It should not be that it is indefinitely just waiting for the critical section to get free. There should be some bounding waiting or bounded waiting. Okay, so that must be there. For that, we have to make few changes to the previous code. Now, what are those changes? Now, there are common data structure we defined before the start. Okay, so there is Boolean waiting n. So there is an n array that we define for n processes. There may be not 1, 2, there may be n processes which are waiting. And then we have int lock. Now this int lock is used for the same mechanism. What would happen? Elements in the waiting array are initialized to false. So everything in the waiting array is false. And lock is initialized to, let us suppose P0 is the first process which tries to enter, come to this section. So it will make pi, let us suppose pi here is 0. So let us suppose waiting I is equals to true. It will make itself as true, the array value true, and key is equals to 1. It set a value key is equals to 1. While waiting I is true and key is equal to 1, what it will perform is updating the key. So update the key is dependent upon compare and swap and lock 0, 1. Okay. So can you tell me if P0 is the first process, what would be the new value for the key? If P0 is the first process, what would be the new value for the key? What I mean to say, while waiting I is equal to true, this already set by the process. Key is already set to 1. Okay. So now this is already 1. This is already set to true. Now while waiting I, which is true, and key is equal to 1, okay, then it will enter into the while. Now in while condition, we are updating the value of key. Now the value of key would be coming from compare and swap function, which would take lock, which is initially 0 and 0, 1, expected value and a new value. Okay. So we pass in these 3 parameters. Now based on the value of 0, lock 0, if P0 is the first process to enter into the critical section, what would be the new value for key? It would be 0. Yes, it will be 0, because what would happen here, you can see whenever this would be called, the previous value of lock is 0, expected value of lock is 0, and new value of lock is 1. So in that case, the temp is equals to 0. Now because value is equals to expected, this value is equal to expected, so there would be a change of the value. Now this value would become new value, which is 1. The new value of lock is 1, but we return the previous value of basically temp, so that was 0. Now if we go here, so because this is a situation, lock was earlier 0, 0, 0, 1, so this function would return key is equal to 0. So when key is equal to 0, what would happen? This process, we get out of this while loop and would make waiting I is equals to false. So this is a section which is stopping wall for the processes. So this particular section, just like the while loop in Peterson, in test and compare, or in test and set, the same thing is happening here. So this while loop is blocking the processes. It will always return the initial value, because we take initial before starting the function. We always take that into temporary variable and it return that value always. So it will always return. Now we will talk about the second situation. Okay, so now this will go out of this loop, making waiting I is equal to false. Here it made true. Now it made it false, and enters into the critical section. This is clear here till now. Okay, let us suppose P0 is into the critical section. P0 is working here at this particular point. Now another process, P1, tries to enter. What it will do? Because I is 1 here, so it will make waiting I is 1 is true, key is equal to 1, while waiting this true, and key is equals to 1, it will enter in here. So what is the value of lock when P0 is into critical section? This is lock is equals to 1. Your P0 is into critical section, lock is 1. Okay, now what would happen to this P1 now? For that, lock value is 1, this is 0, this is 1. Now we go back. Now the new value here is expected value is 0, and this is 1. Now temp would take 1. If value is equal to expected, no, because this is 1, this is 0. No update would happen, not executed. What would be returned? Temp, which is 1. We come back here. Now the new value of key for process P1. When it is 1, what would happen? It go for while loop. Waiting I is equal to true and key is equal to 1. Would it come out of this loop? And it will keep on waiting till the time lock value is not 0. When does the lock value would be 0? When your critical section, when the P0 would be out of this critical section. Is this clear till now? Coming next. Now we need bounded time also and the progress also. Bounded time is there are n processes. After how much time the turn would come for the next process which wants to enter into the critical section. For that, there is this section is written. How this section executes? It will create another variable j, I plus $1. So we are basically, iterating over circularly. While j is not equal to I, because we are going circularly. So while j is not equal to I, and not waiting j. Initial value of waiting array is all false. If some process is not interested to enter into the critical section, for them this will be false. This is false, this is true, not would make it true, and till the time this is there. So what would happen? It keep on jumping. But let us suppose one process has made waiting is equal to 2. Let us suppose P1. So for P1, this would be true, and once this would be true, this while loop would be broken. This while loop would be broken. If this while loop would be broken, what would happen? Now there are two states. If j is equal to I, the lock would be set to 0. Else, if j is not equal to I, waiting j, so waiting of this would be made equal to false. So the process P1, which is basically here on this particular part, process P1 is here in this particular problem, then waiting j would be made false, and it will keep out of, like it jump out of this particular situation and enters into the critical section. So what is happening? Again, this situation, like let me clear this all. So this particular variable, compare and swap, basically it's stopping, and once it is stopped, now this is very clear to us that why while loop is there. Somebody goes out of this I process, the process 0 goes out of the critical section, it now assigns the turn to the next process, and for assigning the next turn to the next process, it uses this particular code where it basically first go to reach the process which wants to enter into the critical section, and then based on the value of j, it will either put the lock to 0 or put the waiting j of that particular process equal to false, so that that process can enter into the critical section. So this is what would happen. So the variable waiting j can become false only if another process leaves the critical section, and only one waiting is set to false, maintaining the mutual exclusion requirement. So basically that would be done. So let us suppose there are n number of waitings, there are more number of waiting. Let us suppose there are 10 processes which are having waitings equal to true, but this logic would enable only one into false and allow that particular process to enter into the critical section out of those 10 processes. So this is how the bounding waiting is handled. I hope it is a bit clear, but certainly you need to so basically we are providing progress here, this mechanism providing progress. Since the progress exiting the critical section set the lock to 0 or set this to false, so both allows the process that is waiting to enter into the critical section. This is progress. Now bounded waiting is when a process leaves its critical section, it scans the array waiting in a cyclic order. It designates the first process in the ordering that is in its entering session,